You're on the rise.
Well, I wish I wasn't.
How about another gear?
What's wrong with my gear?
The ones on your bike.
I want to use this Fatbike as my garden tractor, and besides building a trailer and some other planned additions, I started with fitting the drivetrain with a really low tow gear. A 4-teeth smaller chainring on the front and a 12-teeth bigger sprocket at the back. That will make pedaling uphill a lot easier, but how much exactly? Let's find out. Gears are of course a great invention, and since about 120 years help us not having to operate these funny looking high wheelers, which were slow but still dangerous to ride for the center of mass being so high. But gears not only made modern bikes possible, they also offer quite a deep insight into physics fundamentals. Gears rely on the principle of transmission, which is an example of the golden rule of mechanics, which is an application of the law of conservation of energy, which might well be the most fundamental law humans have yet discovered. Oh man. That means that energy cannot get more or less. Take this to the science of moving things and you get the golden rule of mechanics, which states that the energy to move something is composed of a force F and a distance S, and basically stays the same no matter what. Constant products are much like a teeter-totter. If one number goes up, the other one has to go down, and conversely, in order to keep the product constant. It's also a lot like if you have, let's say, 20 cherries, you can eat 2 cherries for 10 days in a row, or 10 cherries on back-to-back days. The product, so the overall number of cherries, will still be the same. In cycling, work is done by pedaling. The force is applied by your muscles. The distance here is the way your feet are moving on the pedals. Through transmission, you can now use the golden rule of mechanics to choose to either pedal hard, but with few revolutions, big force, small distance, or to pedal fast with little effort. Little force, big distance. This is realized on bikes and cars and a ton of other machines and devices by gears. For example, if I want to go from here to here, I need to do work in order to get my bike up and forward. Doing this with a high gear makes me have to apply a lot of force. These were 5 pedal strokes, whereas with a low gear I have to do a lot of revolutions, so more distance of my feet on the pedals. These were 12. Since 12 is about 2.4 times more than 5, that means that I only had to use 1 over 2.4, which is about 42% of the force with the lower gear. So the force part is up to the rider. He or she can apply as much force as needed or wanted or possible. But the distance part is determined by the gear ratio, which is given by how far the bike moves compared to how far the feet move on the pedals. Let's maybe get some numbers for this. The distance of my feet on the pedals is the circumference of a circle with the bottom bracket as the center and the cranks as its radius. That's 18 centimeters. 2 times 18 centimeters times pi is about 1.13 meters. So while my feet are traveling 113 centimeters, the bike moves forward. Let's see. About 250 centimeters. That means a gear ratio of about 0.452 or about 45%. Let's do the same for a different gear. That would be a gear I would use for going steep uphill. Let's see, 1 revolution. And that's about 130, which is roughly half the weight of the gear before. So 130 now means a gear ratio of about 87%. Since the distance is now only half of what it was before, that means that the force that moves the bike forward is now doubled, because the overall work still has to stay constant. That's why this is a climbing gear. Not a lot of distance covered, but strong enough to get me uphill. So moving my bike from here to here requires work, which though stays the same no matter which gear I use. Let's say I use a force F1, making my feet travel the distance S1, then the product F1 times S1 is the same as the product F2 times S2 using any other gear. This also means that F1 over F2 equals S2 over S1. So by measuring the pedal distances, or since they're proportional, the distances the bike moves forward per pedal revolution of these two different gears, I can now calculate how much more or less force I have to use. But the distance of the pedals or the wheels are obviously influenced by certain factors. Longer cranks would mean more distance on the pedals, hence less force to be exerted. Bigger wheels have the opposite effect. You would need less pedal strokes for moving your bike, thus more force. That is, by the way, the reason high wheelers look like this. They have the pedals firmly connected to the front wheel, making feet and wheels always rotate at the very same speed. On today's bikes and cycling on flat ground, the wheels usually move much faster than the feet. But back then, without gears, the driving wheel had to be huge to grant a big enough gear ratio in order to reach at least modest speed. These high wheelers are also called penny farthings because the wheels had a similar size ratio as a penny and a farthing. If the setup, so crank length, wheel size, air pressure and the like, is kept, then there is an even easier way to determine gear and force ratios. Since they are also set by the numbers of teeth of the sprocket and the chainring used, you can as well count teeth. But how? The chainring determines the number of teeth N1 per pedal revolution. I purchased this unusually small chainring with only 20 teeth, so when my feet do one revolution, the chain is moving only 20 teeth. The number of teeth on the sprocket, N2, tells you how many teeth are needed for one revolution of the bike's wheels. A low climbing gear means using a small chainring at the front and a big sprocket at the back. For example, using a 30 teeth sprocket means that you would need 30 teeth of the chain for one complete revolution of the bike's wheels. One pedal revolution only gives you 20 teeth. The gear ratio therefore is N1 over N2, or 20 divided by 30, which is 2/3 or about 67%. This way you can calculate gear ratios and use those to determine how much more or less force or pedal distance this would translate to, which is exactly what gear calculation tools do. There are some really good ones online. I'll link to one in the video description. You simply tell it the number of teeth of every gear on your cassette, or even choose your cassette model, and it tells you a lot about distance, speed, and also visualizes the distribution of all your possible gears. It can also show why a 21 gear drivetrain doesn't really have 21 gears. For some combinations have the same gear ratio or are very close to one another, or not even possible because the chain would run too transverse. Also, the overall range of your drivetrain is shown as a percentage. 500% means that your fastest gear needs 500% or 5 times the pedal force of your smallest gear. As for my Fatbike, with the addition of the 20 teeth chainring, this means that my lowest gear shifted all the way from here to here. 1.3 meters per revolution instead of 1.9 corresponds to a change in force of 1.3 over 1.9 equals 0.68. Which means that I have to use about 32% less pedal force. That certainly is a big step towards being able to drag a trailer with heavy load up to our garden beds. I have not yet built my Fatbike garden tractor trailer, so I'll be using this as a test cart. These are still left from paving our terrace and are about 5 kilograms each. So 30 kilograms. Not to exceed the maximum load. I cannot use my original lowest gear, but the gear calculator tells me that it has been close to the third lowest on this bike. Let's try. Oof. No chance. Okay, moment of truth, now with the towing gear. Yoo-hoo! Yeah, now that's a lot easier, so about 30 kilos plus the weight of the trailer is quite possible. So much on the principle of transmission. I want to add though that I made some simplifications. Factors like friction, acceleration, air resistance or degree of efficiency have all been left out, but the principle of conserved energy stays true, so more force equals less distance and conversely. See you next time.